he was one of my colleagues before in Alcatel talk, but right now he's in Juniper. Dr. Patrick Tucker, Director of the Strategy and Planning Juniper Networks. His talk is titled Telecom 2020, which is going to be interesting, as you see. And for today, our guest speaker is Mr. Resso from Agilent Technologies. The title of his talk is Investigating Microvia Technology for and higher telecommunications. Mr. Resso is the Signal Integrity Application Scientist in the Component Test Division of Agilent Technologies and has over 25 years of experience in test and measurement industry. He has authored over 30 professional publications, including a book on signal integrity. In fact, he has been kind enough to offer me one of his, a copy of his book, and here it is in signal integrity characterization technique, and I would like to pass it around if you'd like to have a look at it. It's very interesting. So, Mike has been awarded one US patent and has twice received the Agilent Spark of Insight Award for his contribution to the company. He received a Bachelor of Science degree in Electrical Computer Engineering from University of California, Santa Barbara. So here is Michael.
Thank you so much. Very gracious of you to have me here. I'm a local boy. I went to Rancho Picati, graduated in the late 70s, and I went down to UC Santa Barbara to learn how to surf, and I figured I might as well get an electrical engineering degree down there too, so I did that. I work at Agilent. I've been there for about 10 years. I started in the lightwave division doing optics, and graduated into the network analyzer division, which is where I work now. And so I'm technically a marketing engineer, and I do a lot of application notes, going to seminars. I train our field engineers and our applications engineers how to use our equipment, demonstrations. So this is actually a paper that I did last year, and it's on Microvias, which is a interesting technology for backplanes. And so what I'd like to do is keep it very informal, so if you have questions while I go through this, you're welcome to ask questions. And I'll answer as best I can, and we'll go from there. Just a show of hands, how many undergrads do we have here? Okay, and then post-grad? Okay, and I assume the rest are staff and faculty. So, very good. Very good. Oh, great. Great. Okay. Excellent. Excellent. Thank you so much. So, by the way, just one more bit of information about me. When I went to, I guess it was the junior year at the Electrical and Computer Engineering program at UC Santa Barbara, there's a point at which you have to decide whether you're going to go microwave engineering or digital engineering or computer science. And I took one course in field and wave theory, and I decided absolutely not. I'm going digital. Okay? Maxwell's equations were absolutely too much for me. Okay? Now, unfortunately, there's a whole mass of engineers in Silicon Valley today that made that same choice. But what's happening today with these 10 gigabit telecom systems is that as the data rates go up, the rise times of the signal from a 0 to a 1 are approaching 40, 50 picoseconds, which means every printed circuit board structure is now becoming a microwave transmission line. Just what we tried to avoid. Okay, so it's a whole new world, and this area of signal integrity is kind of right between the microwave and the digital. So it's a little kind of a niche now that's actually growing pretty rapidly. So I wanted to show this slide, and I wanted to have any guesses if anyone could recognize what this might be. In general, any guesses? What does this look like to you? What was that?
Servers?
Servers, yeah, it could be. In a general sense, there's a lot of telecom going on with chips on boards into racks and put into a massive parallel computing. It's a supercomputer. In fact, it's one of the real famous ones called Blue Gene, right? This is one that IBM did. And so this is where the state of the art is today. And in fact, one of the, here's another one that looks, I don't know if you can see it very well. Can we get the front lights out to get a little better contrast? There's one here that I really like, and this is,
Other way around.
there you go. This one is actually in Barcelona, and if you look closely, they went in here, and this is actually a church. And they built a supercomputer in a church, and there underneath is all the power and air conditioning. And if you look in some of the racks here, what they did is they built this real powerful supercomputer using off-the-shelf parts only. And so they did massive parallel computing. And in here, all of these cables, there's thousands of these cables. They're what's called InfiniBand cables. And these InfiniBand cables are very similar to what you go and you buy these HDMI cables for your plasma display in your home stereo system. They're just very high data rate cables, but each one of those cables have to be tested 100% for things like differential insertion loss. So what's so interesting is that you can do some phenomenal systems when you do this massive parallel stuff, but what it means is 100% test on the components. So that was the only test we're going to have, so you can relax now. So what we're going to talk about here is telecom system, some of the physical layer overview, what we call physical layer, and then signal integrity and differential signaling and what that means. Talk about 4-port Microvia measurements, and a Microvia is just a small via, right? And a via is when you have a PC board with many layers and you drill a hole through it, you plate it, and that gives you conductivity between the layers. That's what we call a via. And then some Microvia construction, and then how we do a little bit of modeling and simulation. We've got a case study for that. So today, if you look at a typical 10 gigabit telecom system, whether it's one from AFC or Cerent or Cisco, you've got some type of electro-optic components in here where there's transmitters and receivers, and those get put into modules, usually GBIC modules, gigabit Ethernet connector modules. These then get put on the line cards. The line cards get plugged into backplanes, into racks. And then most likely there's going to be some fiber in between rack to racks for the very long distances. So this is a typical system, and what's become the critical link in these systems is the backplane. And this backplane is built into the rack, it's bolted in, and typically the backplane is critical because it has to last much longer than, say, a line card might last. So if you see these companies like AFC that come out with a new product, I've seen, you've got a couple of big boxes over here in one of your labs. They'll come out with a product family, and they'll have a big rack, and they'll sell it to a customer. One of the questions the customer is going to ask is, how long before this becomes obsolete? That's an important question. And so what they do is they have the backplane that's fixed to the chassis be very fast. It could accommodate up to maybe 4 or 5 times the data rate of the current technology, so that in the next year or the year after, when a new chipset comes out from Intel or Texas Instruments, they basically design a new line card, they pull out the old line card, and they stick the new line card in, and they use the same backplane. Okay? So for that reason, the backplanes is kind of the backbone of these systems. And that's where all the critical design goes into. So you get the, all the engineers at a company working on something, they put the real Superman engineer on the backplane, because he's got to make that work the best. Now, when you look into the components in the backplane, you'll notice there's a lot of connectors. I think if you look over here, there's a lot of connectors in here. They're usually in rows. These are actually small modules that get kind of ganged together. But if you just look at one of these, then what you'll end up is with one connector that looks like this. So inside you have some plastic housings that's plastic injection molded. Don't let the plastic fool you. There's metal in here and there's some shielding, and each of these pairs of metallic conductors are very well controlled impedance differential transmission lines. So it's important that these components be designed and manufactured with a lot of precision and with very good design. The whole idea is you want controlled impedance, right? Because if you have some type of channel that goes between a transmitter and a receiver, and that PCB copper trace has any impedance discontinuities or mismatches, as the signal tries to propagate through it, it's going to encounter a big reflection. And so there's going to be reflection coming back to the transmitter and confuse that. You're going to have a loss of energy and rise time as the rest of the signal propagates through the channel. So you have to have components that are very, very well designed. And so we're going to talk more about differential transmission lines, and this is why they're important. In fact, if you talk to many signal integrity engineers today, you ask them, where's the biggest reflection? What they'll tell you is they'll say, the connector. And as we go through this, maybe I'm going to show you why that sometimes is true, sometimes it's not true. Okay, so one thing that if you're a signal integrity engineer today and you're working for IBM or Cisco or Huawei in China, building these super telecom systems, you're going to be designing backplanes, and you're going to have these via structures that are going to cause problems. And what's going to happen is you're going to want to design these vias in such a way that you eliminate any kind of impedance discontinuities. And so if you ever hear a term called a via stub, that's going to be a big design flaw. That's going to be a problem that we're going to want to fix. And so the way a via becomes a problem is, well, let's talk about if it's good. If you design it the way that it's supposed to be used, you've got the high-speed networks coming in on the top layer of a backplane, PC board, and the signal is going to propagate all the way through the via into the bottom layer, and there's going to be no stub. It's going to be one channel with no reflections, and everybody's going to be happy, including the receiver that's going to be receiving the signal. But let's say perhaps that someone inadvertently designed it so that the signal coming on the top layer then exited somewhere in the middle of the stack of the backplane. Maybe it came off of layer 2 or 3. Well, see what happens with this metallic via is this metal is still in the circuit. It's still there. Even though it doesn't go to any other traces, it's kind of dangling out there in space. So when you have a current that's flowing through here, it's going to see 50 ohms, 50 ohms, 50 ohms. Right here, it's going to see 50 ohms there and 50 ohms there in parallel, which we all know is 25 ohms, right? So for a short period of time, it's going to see this 25 ohm transmission line, which is going to be a big capacitive dip. And so there's going to be capacitive loading. This is going to pull down the whole circuit, and your transmitter most likely will fail. It'll stop working the way it was supposed to work. So this is a very common problem today. And so this is something that engineers work hard at to remove. And so what's the solution? Well, the solution today is do it this way on the top. Don't do it this way on the bottom. If you run out of real estate, you have to go to a middle layer. Then there's this thing called back drilling. You can actually physically get a drill of the right diameter, drill from the bottom to remove the metal up to that point. But it's got to be very precise. You have to be very careful that you don't drill too far, or that you drill far enough. Okay? So far, so good? Okay. Also, there's other solutions when you have other types of connectors where you have a standard plated through hole in this configuration, or of course surface mount components will help eliminate this type of via problem. Now, a microvia is simply just a small via with a smaller diameter, and a lot of times it's fabricated not with a drill but with a laser. And what happens is a laser is used because it allows you to get a much smaller diameter hole going through the structure. and that creates less excess capacitance and gives you a more controlled impedance environment.
Okay. You mentioned that in the previous slide that we should later go and then remove from the bottom part the thing which is
the back plane, the back drilling, the back.
Would they do this thing also with the laser? And if they do it, how can they do that quickly so they do not basically make holes?
Yeah, good question. So today, most of the back drilling that's successful is done mechanically with a drill. I think there may be some research going on today in Germany, when I say around the Stuttgart area, where they're playing with lasers doing the back drilling to make it more automated and less expensive. The challenges are, though, is you have to have the laser beam waist be very narrow, and so the power density has to be very well controlled so that you don't have a real long waist. And by that I mean when the beam comes in and the line and it converges, so that you have an area where you're going to blast out that via. You don't want to go too far. So I think the problems have been is controlling the depth of the laser. Good question. And so here's just another example of a Microvia with a surface mount component right in here. So imagine every time you're going to be transmitting a signal through a structure, what you might encounter that's going to cause a reflection. So now let's go to some of the basic signal integrity and the differential signaling that's used for the basic design theory. So today, for high-speed digital protocol, there's all these things: PCI Express, FireWire, Serial ATA, Rapid I/O, HDMI. These are all high-speed protocols that are digital standards. And if you look over time, the bit rate versus time, the old buses used to be parallel in the 80s and early 90s. We finally went to serial buses that are now becoming quite fast, up to 10 gigabits and faster. As I mentioned earlier, when you go to faster data rates, you have a transition from a 0 to a 1 with much faster rise time than before. Well, what happens when this rise time that's faster goes through a same channel with any type of impedance discontinuity like you see here, the reflection is going to be much larger when the rise time is faster. So you're not changing anything in the structure, you're just having faster data rates with faster rise times, and your reflections get bigger. Well, it's these reflections that are causing all the signal integrity problems. And so the frequency domain data that is now being gathered is something that's recognized in the industry, needs to be measured. So imagine that the engineers that are similar to me that are digital in nature, and they go and get a job and they say they're going to design digital boards for a telecom system, and they get a HDMI project and they feel real comfy and they say, okay, you know, this is a board you have to design to work to this compliance specification. You go to the internet and you download the compliance spec that anyone can get, and you go through all the protocol for the testing that you're going to have to make sure is passed. And besides the regular digital domain measurements like skew and rise time and eye diagrams, all of a sudden you see this frequency domain data. You know, it's like, oh my God, do I have to use a vector network analyzer? You know, so this is a big shock. And so this is what's happening today in the industry. There's this underlying need to do frequency domain testing on devices that are inherently digital. So this is kind of where the industry is today, and this is a challenge. And so some of the basic fundamental things that need to be dealt with are differential transmission lines. So why do we have differential transmission lines? Why do we even bother with that type of architecture? Why can't we just route signals with just one line? It used to be good for years and years.
Common mode rejection.
So you get this thing called common mode rejection. So if you have a perfectly designed differential pair, if you have any outside radiation that's incident on this pair, you should have rejection, right? So that's good. You don't have any susceptibility to crosstalk. So this is the idea. And so you get a receiver that can reject the signal, and you reduce the radiation, and So there is definite benefit to going to differential signaling, and if you look at any protocol today that's over, say, 3 or 4 gigabits per second, it's going to be differential. Now, one thing to remember is there is a little bit of downside because the differential architecture requires a slightly different, more sophisticated type of measurement. You can't just hook up an ohm meter and measure resistance. Now what happens with 2 lines, you have a characteristic impedance matrix, and you have mutual impedance between the lines. And so now there's a little more complex things going on inside this differential transmission line. So we're going to talk a little bit about that. Let's say for a moment that you have a differential channel inside an HDMI cable that's going to be hooked up between your HD DVD player and your plasma. And you opened it up, and you're going to actually pretend that you're the engineer that designed it. You want to verify that all the specifications are exactly what it says on the package that you bought at Best Buy. Well, what you would do is you would measure the single-ended S parameters. And so here, if you just look at a 4-port device, which is our differential transmission line, port 1 would go to port 2, and port 3 would go to 4. This is the standard nomenclature that's used. And what we're going to do is we're going to make a family of measurements, and what we want to, what's nice is that we have this thing called a Fourier transform, or an FFT, where we can make one measurement in the time domain. So if we hooked up an oscilloscope to this port 1 over here, and we measured this value T11, which is the signal going in on channel 1 and coming out of channel 1, which would be a reflection, you're going to measure the single-ended impedance, or the single-ended TDR. And if you had a computer and you just did a fast Fourier transform on that, you'd get S11, which is an S parameter. Okay? So there's this nice relationship between time and frequency. And you could either use a VNA, vector network analyzer, and measure this S parameter, then do the IFFT and get T11, or you can go that way. It's up to you. And likewise, if you wanted to verify something called insertion loss, you could measure that with a vector network analyzer, and that would be these terms right here, T21 and 12. And that's the same thing as time domain transmission, which are these terms over here. And just if you go on through, you can see that there are 2 unique matrices, and they each have a one-to-one mapping for all of these wonderful terms. So what we find what's happening is a lot of the digital engineers who have this fundamental understanding of time domain and time domain measurements, but really this S parameter stuff is not so far-fetched. It's not so difficult. You can leverage all of your time domain knowledge and understand what S parameters do for you. Okay, so all of a sudden you're stepping into the world of microwave measurements very, very easily, or at least easier than you thought you could. Now the trick is we want to take all of those single-ended measurements and we want to transform them into differential measurements, because that's how the channel is actually working inside the system. And so the single-ended measurements, if you've got one particular criteria for your device under test, then you can apply what's called linear superposition. And that criteria is that your device is linear and it's passive. So if you have things like printed circuit boards, or connectors, or cables, or IC packages, all these things that are not active, but they're passive, then you can apply this thing called linear superposition, and it's fairly easy to translate your single-ended parameters into balanced parameters. And so that's what we in fact do. And so this matrix in here, this is what all of the digital design engineers today use when they're designing all of these physical layer components. So all these backplanes have to be characterized with this differential S parameter matrix. This is how you would fully describe and model these backplanes.
Mike, can you tell us about the balance? When you say balance, is it that basically you're like partly grounding or something, we call it balance, or what?
So balanced is the term that microwave engineers use to mean the same thing when digital guys say differential. And so balanced basically just means you have 2 lines that are balanced, and there's a virtual ground in between. Yeah. So when I say differential, I also refer to balanced as a sink. So this is kind of the magic matrix here, and this kind of has everything wrapped into one matrix. And this is how all of these differential devices are characterized today. So you can break this since we have here's a basic question. If we have a 2-port vector network analyzer, 1 input and 1 output, how many S parameters do we have? We have 4, right? S11, S22, S21, S12. But since we have a differential device, right, this HDMI cable, we've got 2 in, we've got 2 out, so we've got to have 16, right, 4-port measurement. So here's our 16 differential S parameters, and we break them into quadrants to understand how we can use these to benefit the design of the system. Well, this first quadrant here is all differential input, differential output. This is probably the most important because this is how the component is actually going to function inside the system. This right here, this is our differential return loss, right? It's a reflection. This is the reverse return loss. Here's the forward insertion loss, reverse insertion loss, okay? And if we have reciprocity, which means these two are equal, which we do on linear passive devices, they should look the same. This fourth quadrant down here is common stimulus, common response. This is really not as useful as the others, but we get it for free, so we complete the matrix and also gives us the full model, so we have that data. The most interesting, I think, are these two here, quadrant 2 and 3. We call these the mixed mode quadrants, okay? So mixed mode basically means, in this case, we have quadrant 2, the yellow in the upper right, we have common signal in and differential out. And this describes EMI susceptibility. Why is this important? This is important because this tells us about crosstalk. Crosstalk is a killer of backplanes. It will absolutely stop them from working, especially when you go through these high-density connectors where all the signals are very close to each other. Right? So all of these signals, they're going to crosstalk with each other, and the relationship by which they crosstalk is 1 over the distance squared. So the closer they get, the worse the crosstalk becomes. So when you cram all the signals into a small connector, then the crosstalk is the worst. When you look at this term up here, question?
How is the common in, common out, how is this different than standard S2-port S parameters?
Well, if you just have 2-port S parameters, you don't really have the differential S parameters. You'll just have the 4 ports. So you can't really, I guess you could look at if you had 2 ports and you hooked it up to the input, you could have a couple of the differential S parameters, like you could measure SDD11, but probably that's not how it's used. I'm thinking with single-ended, you just have the 4-port single-ended S parameters. The common here is just, if you have a common signal in and a common signal out, that will tell you how the common signal behaves. But here's kind of the crux of this slide. These 2 mixed mode S parameters, these 2 quadrants, if you have common in and differential out, or differential in and common out, that means you're converting the mode and you're creating crosstalk, which is bad. So you want those 8 terms to be as close to 0 as possible. Okay? Now, what happened? We talked about if you have a perfect differential pair, you have common mode rejection, and that's good. But let's say that when you sent your board up to be manufactured at some PCB house, it came back on 1/2 of that differential pair, there was like a piece of solder, or something happened on one leg and not the other of that differential pair. That's going to create an asymmetry. It's not symmetric at that place. So now, when that incident radiation is on both of those lines, where you normally would be able to reject it, now, that common energy will convert into differential, and it'll ride along inside the channel with the digital data that's transmitting from the transmitter to the receiver. So at the receiver, there's going to be a small delta voltage that is due only to that incident radiation. Well, that's bad, right? And we call that EMI susceptibility. So that's what these 4 terms in this quadrant mean. So up here, if you have any values that are non-zero, then then you'd be able, in these four in here, anything that's non-zero, you're going to be able to figure out you have EMI susceptibility, and not only will you be able to notice the magnitude of the crosstalk, but you'll be able to spatially locate that within the channel when you map it to other time domain data, like at the TDR. And then finally, in this quadrant number 3, this is also a mixed mode parameter, but it's converting the other way around, differential to common. Okay, now what does that mean? How does that cause a problem? Well, we'll think of that same differential pair, but instead of energy that's incident on it, think about the data that's transmitting inside the channel. You've got a differential signal, all these bits are flying through it, but when the signal encounters this asymmetry that we have, then that energy, some of it's going to be transmitted to common, it's going to radiate out. We call it EMI emissions, okay? So what we have here is we have differential S parameters, we have a way to characterize these differential channels, and we also have a method by which we can troubleshoot and verify whether or not we have crosstalk. Okay, so it's very helpful. Okay, so now let's talk about 4-port microvia measurements. So typically in most signal integrity laboratories today, you'll find a 4-port network analyzer. Looks like this. This happens to be a 2-port network analyzer and a 2-port test set that's connected with these semi-rigid cables in front. A more modern one that we have today would have 4 ports all in one box, so you don't have to have a 2-box solution. And you can have both 4-channel time domain reflectometer, which is basically an oscilloscope, an equivalent time sampling oscilloscope, with a couple plug-in modules. And these plug-in modules, they can be either optical or electrical. These happen to be electrical, and they would allow a similar test that a vector network analyzer would use. Has anyone used a VNA before? Okay, that's good. How about a TDR? Time domain reflectometer. Yeah. So it's they're both what we call stimulus response. So it's not like you have signals coming from the device under test. When you do what's called stimulus response testing, your test equipment is providing both the stimulus and then measuring the response, whether it's a reflection response or a transmission response. Okay, so that's a class of testing. So this is what it usually looks like. And these are very useful in doing any type of linear passive device test. So if you do make frequency domain measurements, these are the typical measurements you would find. You'll have dBs on the left-hand vertical scale. You'll have frequency on the horizontal scale, the differential return loss, and the differential insertion loss are the 2 families of measurements. The differential insertion loss, I would say, is the one that's more common and more important to measure first. So that's the one that starts at 0 dB and then kind of rolls off. The reason why differential insertion loss is so important is because, number one, it's the one that's called out in all of the protocols. So if you're this engineer at Cisco and you've got to have a cable design that meets this specification, it has to meet the differential insertion loss spec that's provided inside the standard. And also, what does it really mean intuitively? The way that I think of differential insertion loss is this. It's the frequency response of the device that is seen by the differential signal as it's propagating through the channel. So you can imagine if there's going to be any high frequency attenuation due to a series loss like the skin effect or a shunt loss like the dielectric effect, then you're going to see that high frequency attenuation if you're looking at the differential insertion loss. And that's what this nice little roll-off shows here. And then this other term, differential return loss, is the one that starts at minus 30 dB and it's got all of these spikes in the bottom. The spikes really are not that informative. What you really want to look at when you look at differential return loss, which again, it's just frequency as a function, it's the reflection as a function of frequency, is you want to look at the upper envelope where you have this the top of the curves here. My batteries just went out. But there's an envelope at the top of the return loss, and that's really the figure of merit that you want to use.
Now, how I would like to understand now here the distinguish between the standard and the Microvia. Now, how do you distinguish it now? One of them has more big loss.
Yes.
The Microvia, for example, the can loss. So it is mainly in the upper frequency part.
That's right.
That should be the case. Yeah. Okay.
That's right. So if you compare a standard via with the Microvia, if you look at the differential insertion loss and you go from 0 hertz up to about halfway, which is 10 gigahertz, they're very similar. There's hardly any difference, which is what you'd expect. At lower frequencies, there's not a lot of difference. So if you have a lower data rate design, you can save money by not having to go to a Microvia design.
Yeah.
But when you go to higher data rates, then you're going to have these higher frequency components that must be transmitted through. You cannot afford to attenuate those. In that case, you'd have to go to the Microvia structure that would give you less attenuation of those harmonics. Yeah, good question. And of course, we all know eye diagrams, right? This is kind of the fundamental thing for digital tests. And this is usually done with a signal generator, like a PRBS, a pseudo-random binary sequence signal generator, and you hook it up to your backplane or your digital device under test, and you're pumping data through it. You look at the output of your device with a scope that can measure eye diagrams. Have most of you done that? That's a pretty basic measurement, so you want to make sure you have that kind of experience while you're here. So that's how it's normally done. There are some other ways you can extract the eye diagram that's newer and a little more innovative. You can do a lot of synthesis of eye diagrams from the S parameter measurements. So if you have some specialist software, like we have at Agilent, there's this thing called physical air test system software, and you can make a measurement on a vector network analyzer of this backplane, and you get the differential S parameters. You can save that in a format called Touchstone, which is also a modeling format. So if you're using like any kind of modeling software, you can import that into that environment. But you can synthesize an eye by taking that S parameter, doing some fancy math on it. You can extract the impulse response of the device from the S parameters. Then you can do a convolution with a pseudo-random binary sequence, and then overlay each bit pattern, and that will give you an eye diagram also. So in fact, this is what we're doing today. We're working with the standards committees to try and convince them that it's equal to doing it the old way, except you don't need to have all the hardware, you can do it in software. And so, my prediction is within 2 or 3 years, we'll be doing it that way also. So and the idea is, it's an eye diagram, of course, because you can kind of see the eye in there, right? The little eyeball. The bigger the eye, the better the device is. That means you're not, your 0 level and your 1 level are very distinct. You're not going to confuse the receiver. You've got plenty of margin in between your data. And then in the bottom, you can see where you've got the closed eye, which is less good.
And you see that the Microvia is much cleaner on the right-hand side.
That's right, that's right. So we have the standard via at 10 gigabits per second on the left, the Microvia on the right, and you can see how the eye's bigger. And that's better signal processing. That's a much better signal at the receiver. Likewise, at the higher data rate, 20 gigabits per second, it's very close with the standard via, and then you can see where it opens slightly in the Microvia. So this kind of gives you an idea of how much margin. And when you do mask testing for pass-fail with eye diagrams, you'll put like a hexagon or some type of polygon inside the eye, and if the eye closes and encroaches on that polygon, then you fail. And so those kind of standard masks are given with the standard, so that the people who are testing for this know whether it's pass or fail. Okay, now let's look at some actual construction of Microvias. Here shows some various types of technologies that are used today to create the Microvias. You can have some YAG lasers, yttrium aluminum garnet, There are CO2 lasers that are used. Of course, I mentioned mechanical drilling, and there's actual plasma etching that can be used also. And so there's various diameters of each of these, various aspect ratios of depth to diameter. The dielectric constant of the material that you're ablating is going to be important in some cases and not in others. And so there's a trade-off there. How fast you can blow away the material is going to affect manufacturing, manufacturability. How clean is the via after it's ablated is a big deal. And so there's some various methodologies that are being used. I don't think there's a lot of this being done in the U.S. today. I think a lot of this is done in research. I think there is some production going on in Europe for this sort of thing, but the majority, and by that I mean 80 to 90%, is going to be mechanical drilling. So if you're a Cisco engineer and you have a backplane that needs to be back drilled, you're going to find a house in the U.S. that probably uses the drill.
What are the typical length of this vias, and what is the largest size?
Good question. So I would say a typical backplane has maybe 25 to 30 layers, and maybe is a 1/4 inch thick. And so the biggest backplane that I've seen probably had about 40 layers, and it was about a 1/2 inch thick. So really, it's not all that much.
So you don't have chemical etching in there. Obviously, it's not good. But can you explain why?
For
They're making instead of drilling.
For the original
Yeah.
via construction.
Mm-hmm.
I'm sorry, I'm not sure I
No, it
understand the
doesn't
question.
matter.
I'm familiar with the laser and the mechanical drilling. I'm not sure how they do the plasma, to be honest. If that's what your question was.
So when you have a via which is connecting two inner layers, you drill from the top and the bottom. Right?
Exactly, because you could in fact have 2 via stubs, which is going to give you even more capacitive loading.
So you can do that actually. There's really good drill from the top and
That's
bottom.
exactly what happens. That's exactly what happens. Now, if possible, they try and avoid the high-speed net to have 2 inner layers. Usually there's enough real estate where they only have to have 1 inner layer on a high-speed net. But I have seen it before where they have 2 vias. Yeah, good questions. And then, of course, when you have a connector, like we saw that exploded view, and we transition from the connector, which is a 3-dimensional device, into a printed circuit board, which is pretty much a 2-dimensional device, we have what we call a via field. And this via field is where all the pins on the connector solder into the board. And so this transition is a real critical area for anything to go wrong. And whatever's going to go wrong will go wrong in this area, guaranteed. And so when the routing from the vias to the PCB traces inside the backplane happen, there has to be a lot of care and a lot of design and a lot of modeling that goes into place to minimize things like crosstalk and reflections. And so the things that you would do is you may have more grounding vias to minimize and help shield and control some of the EMI fields to minimize the crosstalk. You may space the high-speed channels further away from each other to get that 1/d² help. So right in here, we have conventional routing versus via in pad. And this is very, very useful technologies when you go into very small boards, like in cell phones. You'll use the via in pad Microvia.
Yeah. When they are, let's say, inserting these vias, how can they make sure that there will be connectivity between these vias and then go to the desired plane with the right connection? How would they be testing all that to make sure that you are really connected and they are not misconnected?
Right. So there's got to be initial design and simulation that's done at the engineering level. And so there's programs that do the design and that take care of the routing, and then at the end of the design, you will export like a Gerber file or something like that that's taken by the PCB vendor, and they import that into their machines that can read that data. So during the design and fabrication, that will have the routing between all the nets and the vias to make sure they're correctly placed. Now once you build them and you deliver them, usually there's an incoming inspection on a certain percentage, and you do exactly the test that we were talking about earlier with this differential S parameters. So you'll measure each channel at the input, and you have test fixtures that I should have brought some with me, but they will allow you to connect to these connectors, that the backplane connectors that you slip the line cards into, but they have these SMA connectors that are the screw type that will allow you to connect the nice test cables that go into the VNA. And so post-processing, those type of measurements are usually either with the VNA or the TDR. And so here we have some interesting pictures of cross-sections. Mobile applications like cell phones do the simple laser drilled PCB. So that's what that looks like. You can do sequential build-up using inline vias, which is just multiple stacking of these structures. And so both datacom and telecom applications will use this type. This is a company, PPC, in Germany that made these. And another combination of sequential build-up with buried vias. And buried vias are like this one in the upper left over there that you cannot see. A buried via is this thing right here, where you don't really have any structure that goes to the top layer or the bottom layer, so you don't see it. It's also called a blind via. So it's constructed so that you have signals going here, in this case, just from layer 3 to layer 4. And so this is how you would fabricate that, and you can see real nicely with the cross-section how they build that. And then if you just look at all the layers from top to bottom of a typical backplane, this is only 12 layers, so I consider this a smaller one. It's got a lot of vias, it's got some blind vias. You can see the pre-preg, which is some of the processing goo that gets put in between the laminations. And this, of course, is also done with design software, and it'll check before you go to layout to make sure that you have continuity through these vias, like you were asking previously about. And this would be like a 6-layer sequential buildup where you have more lamination, more via metallization, conductive patterns. And so this is just one example of the design. And another with more laser drilling, metallization, conductive patterns. Okay, so far we've talked mostly about measurements, but also a big part of what needs to be done today is modeling. It used to be that you would have maybe the measurement team in one part of the lab, then in the other part of the lab you'd have the modeling team, and they really didn't talk too much. You know, the measurement guys would throw the measurements over the fence, or the modeling guys would throw the model over the fence, and they'd look at them separately, but there wasn't a lot of working together. Today, at the higher data rates, you have to have both the models and the measurements, and they need to correlate. So before, when you get away with just one or the other, nowadays with the high data rates, you cannot do that. So you have to speak both languages. And so if there's one thing I would encourage the undergrads or even the grads, when you go and you learn, you have a certain emphasis in a certain area that you get proficient at, make sure that you also brush up on the other areas that you're not so good with, because at that point you can talk to colleagues and optimize your designs and understand the language that they're talking also. So here we have a case where there's 3 different backplane connectors, and they want to see in a particular design case study which one of these is going to perform the best in the system. And they don't have the luxury of building a prototype yet, so what do? You have to do simulation. And you build up these models. So the first setup here is with a surface mount Microvia, with a 0.35 via diameter. Then the second one here is a press fit, but that has through holes with back drill. And then the third case is the SMT with through hole. And so in some way or another, whether you get the model from the vendor or you've taken physical measurements off the connector yourself, you have to be able to get the physical parameters of these connectors and then be able to put that into a modeling engine. And so in this case, we used the Agilent design system, ADS software, and we were able to get some very good indications of near-end crosstalk, far-end crosstalk, and impedance profile. And so, of course, you want to minimize things like crosstalk, right? Crosstalk is bad. It comes from where? From mode conversion, okay? And so, if you here look at the first example, you can see that the SMT pad with the through-hole via is given the most crosstalk. Looks like there's about, I want to say 3.5, 4 millivolts of crosstalk. And so that design is out. And in fact, that's got the worst far-end crosstalk also. And so, and you look at the impedance profile, if you had a perfectly flat 100 ohm differential impedance from start to finish, that would be the best differential transmission line. That's what you'd like to have. But of course, all these things are fighting against you. You have reflections and vias and stubs and all that sort of stuff. So here, you can do the simulation and have a good idea to predict which of the designs you should use and which components you're going to choose for your work. So when you're finally in the system level of the backplane with the daughter cards, you can picture exactly what the signal flow is going to be. You have the transmitter with on the left-hand side in a chip package. This could be a SerDes, a serializer, deserializer chipset, and you've got the differential data being transmitted through the daughter card, through the via field in the daughter card, into that connector, then into the via field for the backplane, then through the backplane, which should be a very long differential impedance that's very well controlled, and then in through the other connector and out. Who's actually done a TDR before? I saw someone in the, you've used a TDR before, right?
Yeah.
So TDR, I'm going to draw a picture here maybe. Do I have any markers? I'm kind of unconventional here, but because the idea is if you can get like an intuitive feeling of if you can be the signal, right? If you can just get inside that channel and imagine each impedance discontinuity that you're going to go through. You know, I apologize for that. What I was going to do.
It's going to be
okay.
You have to get a set of marker, but
is this okay to write on this board?
Yeah, it's a dry erase.
Okay, so if I'm going to imagine that I'm the signal and I'm going to propagate through this channel, because this is my backplane. You know, my job as Cisco right now depends on it, right? So this is a really important thing. Thank you. So if we have a TDR trace, instead of having voltage versus time, a TDR, time domain reflectometer, is just an oscilloscope that's designed to read impedance versus distance. Okay? And so if I have a perfect differential transmission line, I'm going to have 0 ohms and 100 ohms, and I'm going to have this, right? So if the world were perfect, this is what I would have. When I have this sort of setup, what's going to happen? Well, I'm going to start at the chip, and I'm going to go through the chip package, and that little tiny leg that goes from the chip to the daughter card, there's going to be a little bit of excess inductance, and that's going to do this, give me a little more impedance. And then when I go into the daughter card itself, between the leg of the chip package and the via field on the daughter card, I'm going to have a little transmission line that may be close to 100. But then I'm going to get to this via field on the daughter card, right? This is where the connector plugs into that daughter card. What I'm going to have there is for one connector, that one connector on the left, I'm going to have 2 big reflections. Okay? And where are they going to come from? They're going to come from the transitions between the connector and the PCBs. One from the daughter card PCB, one from the backplane PCB. We call these areas the via field. Yes?
Why you consider your line to be 100-ohm line?
Well, no, I give that as an example if I have the perfect differential transmission line. Okay? But if I design this channel, those target impedances today are 100 ohms differential. So on my daughter card, it better be darn close to 100 ohms inside that differential pair. Right? So that's my target. But I have all these problems that are going to cause problems for me. So what I'm trying to show is what this impedance profile will look like if you were the signal propagating through the channel. Okay? So that there's going to be two big reflections in that connector, and they're going to be, do you think they're going to be excess inductance or excess capacitance? It's one or the other, right? They're going to be capacitive. That's exactly right. So the via field on the daughter card is going to be right here, and the via field on the back plane is going to be right here. And inside, there's going to be this differential transmission line that's really short. That was like that connector that we had the exploded view, and it was a well-controlled differential pair. So we're going to have the first via field on the daughter card with a big capacitive discontinuity. And then I'm going to go through the connector itself. It's going to be a short transmission line, which is fairly well controlled. Then I'm going to go through the backplane via field, another capacitive discontinuity, and then I've got my backplane. And my back, yes?
There's 4 minutes left.
4 minutes left? Okay. So I get to my backplane. It's going to be a long differential transmission line. It's going to be pretty close to 100 ohms. Then my other connector is going to have the same sort of arrangement here, but my rise time is going to be a little bit less because of the attenuation in the backplane, and then my other daughter card. So what most engineers that are good do their designs is they imagine by looking at structures, or they use instrumentation like TDRs to measure the impedance profile, so that when they envision a channel like this, they're going to see exactly what the signal sees. And what that allows them to do is to decide where the problems might be, and then how they might remedy those problems. Okay? Does that make any sense?
Can you null out the capacitive of the vias with some sort of inductor, kind of make it resonate at the transmission frequency?
So what you'd want to do to compensate for this is you'd want to you'd use your old transmission line theory of Z naught is equal to L over C, the square root. So when you have series inductors and shunt capacitors on your differential transmission line, that here you would want to add some inductance or remove some capacitance. And so physically inside the via field, what they do is they usually remove capacitance by making the antipad smaller. So there's a structure around that via inside the backplane that they would actually go and they'd redesign. So that's how that works. So this is kind of actually the fun part of doing the engineering. And so this is a typical model of a backplane using ADS, and each of these components are parameterized. So those little text in there describes all the parameters and the physical geometry of each of those components. And that's how you define a model. And the simulation and measurement validation. Remember I mentioned you want to correlate the measurements with the modeling. And so this is one of the ways that you do that with the oscilloscope again. And this is just an example of looking at the measurement versus simulation of the microvias versus the standard vias. And on the left, you can see the microvias have a much more open eye than on the standard vias on the left. And then top to bottom, you can see that there's pretty much good correlation between measurements on the top, measurements on the bottom and the simulation on the top. And I think that's pretty much it. So here's just an example of some of the equipment that we used in the experiments. And And in the top we have the P&A is really the same thing as a VNA. P&A is Performance Network Analyzer. Software running on a laptop, and then the test set underneath with some other kind of cables and ecal units. And then below is the TDR scope with the software. And that's it.